In this video, I will show how to add a small solar panel to a motorcycle in order to keep the battery topped up. This might be useful in case you can't park your bike near a power outlet to trickle charge it. I will start with the mechanical aspect, though this will be a bit dependent on your own setup. My top case is a GV Tracker Monarchy one, which has this annoying pattern sticking out on top, so I had to use a tiny panel that fits in between. After searching on Aliexpress, I found one, which is advertised as being a 10-watt panel, but I think you will be glad to get 1 watt out of it. I will add a link for it in the description, but let's be clear, I would not necessarily recommend this particular panel. If you go looking for a different panel, you do have to take care to pick something intended for a 12-volt system, so with an open circuit voltage of around 14-15 volt. Less than 13 volt and you will not be able to charge your 12-volt battery at all. More than 15 volt and you will not be near the maximum power point of your panel when connected to a 12-volt system, so you will be wasting power. An overvoltage mismatch can be solved with a more advanced solar controller, but I want to keep things as simple as possible here. I removed the existing wiring from my panel and soldered on my own wires, which I routed through the hollow GV decorations, then a flexible part where the case opens, and then to the bottom via an extra guide I melted on the existing plastic to end in a waterproof connector. For melting on some extra structures on the casing, I just used a cheap soldering iron with a flat tip and some scrap plastic. As long as the plastic is of the same type as the top case plastic, you can melt it on, a bit like a 3D printer does. In this case I used ABS as indicated on the label inside. Just make sure to do it in a well ventilated area or outside, as the fumes are toxic. The panel is just glued on the box, for which I used Tech 7 adhesive. But do not press it all the way down, as you want some airflow under the panel so it does not get too hot. And I'm also still looking for a better system than the connector I'm using now, as I sometimes forget to pull it out and I just rip off the connector when removing the top case. Something magnetic or with pogo contacts, but I haven't found the ideal solution yet. With that part done, you could just hook up the solar panels directly to your battery, but there are two problems with that. The first problem I can easily demonstrate. Here I have a multimeter connected to show the voltage and the current, with the positive current meaning the battery is being charged. I start with the solar panel disconnected. You see that the open circuit voltage is a bit lower than 14 volt in the current weather, which is perfect. If I made the connection, the panel voltage becomes 12.65 volt and about 20 milliamps of current are flowing towards the battery. But if I cover the panel, you see a negative sign appearing, so the current reverses, meaning the panels are actually a load when there is no sun shining on them and they would discharge the battery. So that is the first problem that needs to be solved. Note also that I'm only getting about 250 milliwatts here, so not quite the 10 watt advertised. Partially it can be explained by the sun not being an optimal angle with respect to my panel, but still. I'm not going to try and demonstrate the second problem, but with a direct connection it is of course possible to overcharge your battery. On sunny days, when the sun is in an optimal spot, the panels can produce a higher voltage than what is healthy for the battery. Chances are low that it's gonna be a real problem with the low wattage of the panel, but I prefer to not take any risk. So we need to throw in a bit of electronics to deal with those problems. One fast solution is to hook the solar panel and the battery to one of those cheap solar charge controllers like the one I have here. But this thing uses about 10 milliamps by itself, doing absolutely nothing. So let's make a better solution step by step. To block the discharge path with a shaded panel, we simply need to put a diode in series with the panel. A diode is a component that allows current to flow in only one direction, exactly what we need. It does come with the disadvantage that we lose about half a volt over the diode, so some energy is lost here into heat. You could make it more efficient by using an ideal diode, but I'm not going to worry here about those lost 50 milliwatt. To prevent overcharging, we need to add a switch to open the circuit when the battery voltage reaches a certain level. Of course, we want a switch that can be operated automatically, which is something you can do with a MOSFET. I am using a pretty beefy one here, as it can switch up to 48 amps, which is totally overkill for this application, but it is one I recovered from an old motherboard I happen to have lying around. If we look at its datasheet, the N-channel MOSFET used here acts as a closed switch if the voltage difference between the gate and the source is above the upper threshold of 2.2 volt. and it becomes an open switch when that voltage gets below the lower threshold of 1.3 volt. So now we need something that can generate that toggling gate voltage based on the battery voltage. For that, we can use a TL431, which is an adjustable shunt regulator with an internal reference of around 2.5 volt. What does that mean? Well, when the voltage at the VRF input rises above the internal reference voltage, so 2.5 volt, the chip starts shunting, so conducting a lot of current. And when the VRF input voltage drops lower than that internal reference voltage, it stops conducting. Since we want to flip the switch not at 2.5 volt, but at, for example, a battery voltage of 13.3 volt, we need to connect that reference input to a resistor divider. This is a simple trick to convert a higher voltage signal into a lower voltage signal that tracks the higher voltage. The conversion factor is given by the division of the bottom resistor by the sum of the two resistors. So in this case it will be 30 divided by 160, which is about 0.19. If our battery reaches 13.3 volt, then the VRF point will be at around 2.5 volt. So in other words, when the battery is around 13.3 volt, the shunt will start shunting. Perfect. So how do we hook up the regulator to the gate of the MOSFET? With another resistor divider like this. Let's see how this works. If the input reference voltage is lower than 2.5 volt, the regulator will block current, so all the current will have to flow through the 10K and 2 times 220K resistors. Note that there will be a little bit of current flowing through the gate as well, but we can ignore this for this calculation. The MOSFET's gate voltage will be at more than 6 volt, way more than the upper threshold of 2.2 volt, so the switch will be closed and the panel can charge the battery. If the input reference voltage is higher than 2.5 volt, the regulator will conduct current, but it will still have a minimum voltage of 2 volt over it, as specified in the datasheet. So now that 2 volt will be halved by the resistor divider, meaning we have 1 volt at the MOSFET's gate, which is below the lower threshold of 1.3 volt. So the MOSFET will be open and charging will stop. So the circuit does what we need it to do, but a few things still need some explanation. As soon as the MOSFET opens, the yellow part of the circuit will get a voltage lower than the negative battery voltage, as it will go to a voltage equal to the battery plus minus the open circuit voltage of the panels. So this means that relatively to the anode of the TL431, the VREF is going to be even higher than when the MOSFET was still closed, and you get a kind of latching effect till the panel gets in the shade and the VREF voltage drops again below 2.5 volt and everything resets. To help speed up the transition through that 2.5 point, a bit of positive feedback can be added in the form of this 1 mega ohm resistor. It will help push up the VREF point relative to the anode as soon as the effect starts. I suspect it's not really necessary as you already have a kind of positive feedback loop with the yellow part dropping in voltage, but it won't hurt either. The 10K resistor is chosen like that because in order to operate as an active shunt, the TL431 requires a minimal current of up to 1 mA. With the 2 volt over the TL431 when it's shunting, that leaves 11 volt over that resistor. Divided by 10K gives a bit more than that 1 mA. Normally there should be enough margin as it's typically only 0.4 mA, but it's best not to go higher than the 10K. And you want of course to use as high as possible resistors to limit the current consumption of the circuit. There is also a capacitor on the VREF input signal in order to stabilize that signal. And finally, when the panel is in the shade and not giving energy, but the battery is still at a voltage higher than 13.3 volt, and thus the MOSFET is in an open state, the system is still being fed by the battery. This is because the MOSFET also has something called a body diode, as I have drawn now explicitly in the circuit. This body diode allows current to flow in the indicated direction and thus keep everything energized. I found this circuit in an EEV blog thread I will link to in the description, so all credit goes to member 0999. I did reduce the cutoff voltage to 13.3 volt, which corresponds more to the float voltage of a lead-acid battery charging cycle, which seemed healthier since we may sit there for a very long time. As I made one board that also contains a circuit to control my fog lights with my high beam switch, the circuit board I will show next also has some extra stuff related to that functionality. but I will not discuss the fog lights part further in this video. Since I do not have a mini CNC milling machine, nor a laser etcher, and I don't want to mess with etching chemicals, and the board is very simple, I just cut some traces with a knife to make the PCB, and drilled some holes for the connectors. I start by rearranging the circuit a bit to match a possible physical location of the components and create a layout in a drawing program. Then I cut the layout in a board and solder on the components. Since the fog lights pull quite a bit of current, I also made some cable eye connections with screws. To protect the board's copper layer there, I just soldered on some cut-off cable eye endings. During testing, I did notice the voltages I measured at the MOSFET's gate were about a volt lower than what I had calculated. But this is because the TL431 shunt does not perfectly block the current when its input is below 2.5 volt, as shown in the datasheet in a graph I initially overlooked. For example, at 2.2 volt at the VRF input, it is already shunting 210 microamps. That current comes via the 10K resistor and causes a higher voltage drop there, which also results in a lower voltage at the MOSFET's gate. But it is still more than 5 volt, which is plenty to keep the MOSFET closed. It does mean the circuit consumes about 10 times more current than if the shunt would have been perfect, and we would only have 28 microamps running through the 10K resistor. But the total current consumption is still only about 0.3 milliamps, so nothing to worry about. Apart from that, everything works as expected. I enclosed everything in an as good as I can sealed box to avoid water and condensation problems, connected all the cabling to it, and abused a cable mounting point to attach the box to. Now on to some real-world testing. A first test with the panel covered shows that the current consumption of the board is around 300 microamps, which, as I already discussed, is mainly the current loss going through the shunt as we approach the 2.5 volt threshold. On a clouded September day, the panels produce a rather pathetic 5 mA, or about 60 mW. On a sunny September day, it gets a bit better, with 30 mA, or about 350 mW of power. To simulate a very nice summer day, I hooked up a power supply instead of the panels, and the multimeter is now measuring the voltage over the battery. The voltage difference between the multimeter and the power supply is the voltage lost over the diode and also a tiny amount in the transistor. To quickly test the battery overcharge protection, I will just increase the power supply voltage, which leads to a higher voltage over the battery due to internal losses. As you can see, the disconnect happens at a voltage a bit higher than the 13.3 volt I calculated theoretically. It seems to be around 13.8 volt. Which is a perfectly good cutoff point, but I don't have a good explanation at the moment for the increased value. While it is theoretically possible it is due to the component variations in the resistors and the VRF point, I don't really think that's the case, but I would have to open everything up again to do some more measurements. If I figure it out in the future, I will put the explanation in the description. In any case, the system works to protect the battery against overcharging. I am a bit disappointed though with the power output of this particular panel. If I do a quick back of the envelope calculation with the panel size I have here, and based on a lowball estimate of the power I get from my full-sized panels at that time, I think at least 2 watts or 160 mA in those conditions is not unrealistic. I will try in the future with some other panels, or maybe even build one myself. I will put an update in the description if I find something better, but for now this one will have to do.